Welcome to another edition of Coonrod's Corner. Today's topic, what should be considered for optimal high-frequency impedance control? Now here's your host, John Coonrod.
Hello and welcome to Coonrod's Corner. My name is John Coonrod. I am a Senior Market Development Engineer for Rogers Corporation. I'm going to spend the next few minutes talking about impedance control and specifically some of the variables involved with impedance control and how to optimize that. To begin with, the printed circuit boards that are used in high-frequency applications have become more and more complex over the years and more demanding. And when it comes to impedance control, they are definitely getting more demanding as well. So impedance control at one time was thought to be good at plus or minus 10%, and now plus or minus 5% is more common, in some cases even less than that. And understanding the variables involved with impedance control is very good for the designers and the printed circuit board fabricators to be aware of. The potential variables involved with impedance control is dependent on the circuit construction itself. And three of the constructions I'm going to talk about are the microstrip transmission line, the grounded coplanar transmission line, and the strip line circuit. And each one of these have their own unique set of concerns for impedance. They do have some common topics for impedance as well, as you'll see, but they also have some unique situations due to how the circuits are actually made. My first example is looking at microstrip transmission lines, and I've used a very common electromagnetic modeling software to look at impedance models and vary in just a few of the critical parameters. Now what I found was the thickness of the circuit is very important, and because of that I've actually modeled a thin circuit and a thick circuit on the same material as shown in the table here. The table of information on top is for the thicker circuit, 20 mils thick, and the table on the bottom is for the thinner circuit, 10 mils thick. And you can see there's a variety of different parameters being looked at. The first row on each one of these tables is the baseline, and that gives the substrate thickness, copper thickness, conductor width, and characteristic impedance. And then after that I change this one variable and I see what kind of difference there is in impedance. And you can see that the outstanding variable that has the biggest impact anyway is the substrate thickness itself. And that's regardless whether it's a thin or thick circuit. So the tolerance of the substrate thickness is very important. It is the most important topic for impedance control. The next one would be the conductor width, and then after that would be the copper thickness. And finally, the dielectric constant tolerance. In this case, the material I'm using has a tolerance of plus or minus 0.05, which is considered very good for high-frequency materials, and you can see that it has the least impact on the impedance variation. Now let's consider the grounded coplanar waveguide structure. The grounded coplanar waveguide structure has very strong electric fields on the coplanar layer, which is the ground signal ground layer on the top copper layer. And because of that, you have more influences related to the circuit fabrication where the copper plating thickness can vary more the impedance. And the reason why is because the sidewalls of the neighboring conductors between the ground signal ground, the sidewalls basically will be taller or shorter depending on the copper thickness. So copper thickness variation that's normal in circuit fabrication, that variation of copper thickness can impact the impedance. The grounded coplanar waveguide transmission line has another influence, and that is the trapezoidal effects. The trapezoidal effects is a common influence for printed circuit board fabrication. So if you would look at a microsection or a cross-sectional view of a circuit, what you'll find is the conductor is not rectangular. It usually has some angled sidewalls, so it has more of a trapezoidal shape. And in the case of the microstrip transmission line, the trapezoidal shape has very little influence on the impedance. But in the case of the grounded coplanar waveguide, it does have more influence on impedance. And that's really because on the coplanar layer where you have the ground signal ground, the spacing between the signal and the ground, if those sidewalls are parallel, that's different than when those sidewalls are angled away from each other. And the angled away would be the variation due to the trapezoidal effects. So that's one thing that needs to be considered with this type of structure. The next structure I'm going to talk about is the strip line circuit. The strip line structure has the same variables as microstrip and the grounded coplanar waveguide. However, it's got an additional variable, and that is the thickness tolerance, and that's above and beyond the material tolerance. So all materials have some tolerance for the thickness. However, in the fabrication of a strip line, you have to go through a bonding process to adhere the different layers together. And this bonding process can vary the thickness of some of the layers. And that is part of the normal printed circuit board fabrication, so there is some tolerance associated with that. And as mentioned before, the thickness of the circuit is a large influence on the impedance of the circuit. So understanding the circuit fabrication and the thickness control they have in bonding these materials can be very important to understand. This concludes this session of Coonrod's Corner. Thank you for watching.
For additional information and technical tools, if you are not already a member, join the Rogers Technology Support Hub and gain access to calculators, technical papers, and more of Coonrod's Corner and other informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.